So now we'll start speaking about annuities. What are annuities? Annuities are very important instruments which we encounter on daily basis in our lives. For example, your mortgage payments, that could be an example of annuity. Your car payments, let's say lease or finance for a car, that can be an example of annuity. But we'll go ahead now and investigate mathematical aspects of annuities. We'll start with a very simple example to motivate our discussion. We'll explore that simple example, after which we'll move on to speaking about annuities in depth. So in this example, let's start with this. So let's draw a timeline. On this timeline, 0 will represent today. It's time 0. So then we'll have plus 1 year, which is 1 year from now, plus 2 years, which is 2 years from now. So then it will be plus 3 years, plus so on, and then plus 10 years. So in this timeline, I basically put various dates, and there are 10 of them, which stand for 10 years into the future. Okay, let's say after the end of the first year, you decided to put your first payment into a bank. Let's say that payment is going to be $100. Okay, so at the end of the first year, you put $100 into your, let's say, savings account. So at the end of the second year, you also will put another $100 into your savings account. Now, at the end of the third year, you will put $100 into your savings account, and at the end of 10 years, you also will put $100 into your savings account. So in this case, you just come to a bank at the end of every year and put $100 into your savings account. Pretty straightforward stuff. Well, we can ask now a question. How much money will you have in your savings account at the end of 10 years? So right here, how much money will you have? How much money will you have accumulated by the end of 10 years? Of course, from what we talked about before, you cannot just say that it's going to be $1,000, right? So it's not like that you can add $100 from that first payment, then $100 from that second payment. So you cannot just add them up. Why? Because there is such thing as interest, right? So each payment that you put into the bank will earn some interest over the duration of time that the payment is there. For example, let's speak about this first payment. Okay, so once you put this first $100, that first $100 will grow into that in that account for 9 years, right? So it will be 9 years worth of interest that you will accumulate. So then, by the same token, the second payment that you put into the account will grow for 8 years. So it will accumulate 8 years worth of interest. And of course, the same process will happen for every payment that you put. And you need to realize that the last payment that you put at the end of 10 years will not give you any interest, because the question about accumulated value after the end of 10 years coincides with that time that you put your last payment. So your last $100, of course, will not give you any interest, because you'll put that last $100 and that's it. And that's when you actually begin to ask that question about the accumulated value at the end of 10 years. Okay, so first a little bit of terminology, okay? So let's call this ultimate future value, so that amount that you accumulate at the end of 10 years, let's call that future value of annuity. Future value of annuity. Or for short, I'll just call it future value of A, like future value of annuity. Now, what is annuity? We'll define annuity maybe a little bit more formally soon, but for now I'll tell you that annuity is this structure where you pay the same payment at the end of the same period. So, for example, payment here is $100. The payment doesn't change; it's the same payment that you pay, and the periods are also the same. So, at the end of the first year, at the end of the second year, so there is always 1 year between payments. So, for now, let's call that structure annuity. So, what you see here is annuity, and future value of annuity is that future value that is at the end of of that structure. So now, simply speaking, this future value of annuity is the accumulated amount at the end of 10 years of this 10 payments. Now, if we try to write down this future value of annuity, you will realize that this future value of annuity will consist of the following components. So the first component will be future value 1, which is the future value of this first $100, your first payment, which will grow for 9 years, right? So then it will be plus future value 2. So what is this future value 2? Future value 2 is that future value of the second payment, which will grow for 8 years. Plus, of course, there will be future value 3 and so on, so on, so on. So plus that last payment, which is your last $100 payment, right? So there will be, of course, 10 terms here. If you add up those 10 terms, you will get that future value of annuity. Let's write down this a little bit in more detail maybe. Now I'll replace this future value 1 by actual calculation. So future value of annuity is, what is this future value 1, right? So that's $100 invested for 9 years. So 1 plus 0.02. Okay, so you know what? Why I'm saying this 0.02? Because I'll assume for now that the rate is 2% compounded annually, right? So in this situation, let's say the bank gives you 2% compounded annually for your investments. Now, for every investment that you pay into that bank, you will earn 2% compounded annually for the whole duration of this structure. So that's why, assuming that it's 2% compounded annually, future value 1 is that future value of this first $100 payment for 9 periods, or in other words, for 9 years, right? So plus future value 2. So that will be your second $100 payment, 1 plus 0.02 for 8 years, right? So you see, so these are just those future values which are written as they should be using the formula that we already know, which is future value is present value, 1 plus I, n, right? So that's the formula we already are familiar with from our previous discussions. So we use this formula for future value to find each of those future values, right? And plus $100, which is this last $100. So you can imagine that there are here 10 terms, which if we calculate separately and add up, we will get that future value of annuity. Of course, that's a lot of work to calculate this. Maybe not so much in this example, but still it's a lot of work. But you see, if this example had 20 years, it would be even more work. But now, if these payments were at the end of every month, for example, for 10 years, that would be 120 payments, and that would be, this future value of annuity would contain 120 terms. You can realize that it's a lot of work to calculate this. So, of course, we could take Excel, and basically in Excel we can find each of those future values, you know, and put them all in one column and add them up and find future value of annuity. So that we could do, but still that's something which is not that straightforward, right, to deal with so many payments. Luckily for us, in mathematics, there is a formula that has been developed for these kind of future values of annuities. This formula basically allows you to calculate that future value in one shot. Okay, so let me write that formula for now, and let's see how that formula would work. Remember that later on we'll deep deeper into the discussion of that formula, and we'll learn when it can be used directly and when sometimes you need to do some modifications for that formula to work. But let me first write that formula down, okay? So we're not going to calculate this now by hand. As I said, you could do that in Excel if you wish to. I just showed you for now how this future value of annuity would look like if you were approaching this directly. Now we'll calculate this future value by a different process, which is much better and much faster process to calculate future value of annuity, right? So let me erase this. So the formula I'm talking about, that shortcut formula is this. So we'll just write it like this. Future value of annuity is PMT, which stands for payment of annuity. In this case, this payment is $100. That's what I'm referring to. So that's multiplied by the bracket 1 plus I into exponent n minus 1 divided by I. Okay. Let me close this bracket here. Okay. So that's the formula I'm referring to. Okay. So that's the formula. It will be one of our most important formulas going forward when we talk about annuities. But let me discuss the components of this formula for now. Okay. So this payment is the payment, right? So in this our example, this payment is $100. What is this I? I is already something we are familiar with. I is the periodic rate. Okay, so in this particular problem, we took 2% compounded annually as our rate, and payments are happening at the end of every year. So this I, in this case, will be just 0.02, right? So now n is the total number of payments in the annuity. So in this case, we have 10. So n would be 10 here because there are 10 payments. Once again, we'll return to this formula later on. Remember, that's first example which sets the stage for our discussion. We'll consider other examples where things will be more complicated. For now, that's just for you to have that first exposure to look at that, formula, okay, and understand its components. So how will we use this particular formula for this particular example? Well, so instead of PMT, I can put $100, right? Because PMT is $100. Now, instead of this I can put 0.02, right? Instead of this n, I can put 10. And it will be here also 0.02. That's it. You see, I'll take this formula and I'll put some values in. Now, you should be a little bit careful. As I said, in order for you to learn to use this formula properly for different kinds of annuities, still you will need to understand a little bit more stuff, which we'll discuss. For now, in this particular example, that is how the formula would work. You just put $100 instead of payment. You put 2% or 0.02 instead of your I, because it's compounded annually rate, and period here is 1 year, and there are 10 years or 10 payments, therefore it's 10 here. Okay, so now if we follow BEDMAS very carefully and try to calculate this, we will come up with the future value of annuity. So how do you follow BEDMAS in this case? Well, brackets first, so it will be 1.02, of course, right? So then exponents, so then 1.02 into exponent 10, okay? So then, by the way, speaking about brackets, keep in mind that numerator and denominator of the fraction each are considered to be in a bracket, right? So the bracket is not written here, but in reality it's assumed. So it's assumed that actually there are, brackets here. So now in the bottom there is nothing really to worry about, nothing to calculate, because there is no expression here. But sometimes when you have a fraction which has a complex numerator and complex denominator, keep in mind that the whole numerator is actually in a bracket and the whole denominator is in the bracket. But these brackets are not written because this fraction is, the convention is that once you have a fraction like this, you kind of assume there are brackets there. So why I'm saying that? Because once you find this bracket, which is 1.2, take it into exponent 10, then next you have to subtract this 1. So that will complete calculation of the numerator. Then you will divide that numerator by the denominator. So after you calculate that, then you will multiply by 100. So let me go ahead and do that. Okay, so this, if I calculate this, it will be 1094.97, rounded to 2 decimals, 1094.97. And that, I can now remove this, red border, just for cleanliness. Okay, so now, if I calculate this, it will be 1094.97. So remember that future value of annuity that I wrote earlier, which was the sum of 10 terms. So if you add up all those 10 terms, you will get actually the same future value. Okay, so it's 1094. So now, look, if you just add up those $100, you will get, of course, $1,000 if you disregard interest, right? But this 94.97 means that you actually earn in this arrangement, you earn $94.97. Okay, so that's your interest in this example. Now, to put this long story short, if you have an annuity, this kind of arrangement when you have the same payment over the same time intervals, also I should add the rate should be the same in the whole, over the whole term of this arrangement. If you have an annuity like that, it is a very straightforward process to calculate it in one shot, right? Using one formula like that. And we just saw how this works in this example. Later on, we'll dive deeper into more examples where we'll calculate annuity future values and also present values for various more complex situations. With the same style as we did with the future value of annuity, we will introduce now what the present value of annuity would look like. Again, let's have a timeline. So I have this time. Let's also put on the timeline time 0, which is today. Okay, so then we'll have plus 1 year, which is 1 year from today, plus 2 years, 2 years from today, and so on, plus 10 years from today. Now, in this particular example, we'll be talking about a situation of finding present value of annuity, but we need to understand first what it means for the annuity to have present value. What is that? Okay, so assume that just for now it's your timeline. There are 10 years in this timeline. And let's say today you actually take a loan. So at time 0 today, you take a loan, for example, right? And that loan we'll call present value of annuity. So that loan could be, for example, you take a loan to buy a car, right? Or you could be taking a loan to expand your business, whatever, it doesn't matter. So you today take a loan, some amount, which you have to pay in the course of the next 10 years by paying the same payment at the end of each year for 10 years, right? So we do that very frequently in our modern finance, right? So what you can encounter this arrangement when you come to buy a car, right? You don't pay the full amount of the car. Unless you want to, right? You can pay, of course, full amount. Or you can pay cash price for the car. But most of the time, what we do is we pay for our car monthly in future. So we take the car from the parking lot. We already drive it, but then we pay for this car every month. So assuming this situation, you have taken some loan for which you have to start paying only at the end of the first year, and then you will continue paying for the next 10 years. So for this particular loan, you pay first $100 at the end of the first year, right? So then you have to continue paying at the end of the second year, $100, and so it will go, and you will pay your last payment at the end of 10 years, which also will be $100. So in order to pay for this loan, which we call for now present value of annuity, so that's the name for that loan, present value of annuity. For that loan, we are going to pay $100 at the end of every year for 10 years. If there was no interest rate, of course, for that loan you would pay $10,000 in total. So, which means that your loan would be $10,000 if there was no interest. But there is interest. Let's say that interest is, in this example, let's take it 5% compounded annually. Okay, so interest rate charged on that loan is 5% compounded annually. Well, we have a question now to ask: how much is that loan? What is that loan amount, right? So of course you can realize that in order to find this loan amount, let me write it down here as present value of annuity. That's loan amount. It is equal to present value 1, which is the present value of this first payment, because your first payment is 1 year from today, right? In order to find this present, in order to find how much that $100 paid 1 year from now is as of today, you have to find present value of this first $100. So then you will have to find present value of this second $100, and so it will go. And also you have to find present value of this last $100, right? So this loan amount will be the sum of 10 present values, okay? So it's as if you're taking actually 10 loans today, which all sum up to that, a bigger loan. But now if we try to substitute actual calculation for present value 1, present value 2, and so on, we will get this result. Okay, so present value A will be, now what is that present value of this first $100? It's 1 plus 0.05 minus 1, right? Why is it minus 1 here? Because now I'll remind you that present value is future value 1 plus I minus n, right? So that's our formula for present value under compound rates. Okay, so present value of this $100 is 1 plus 0.05, which is I, minus 1, because it's only one period so far here. Now, if I find present value for the second payment, it will be 100, 1 plus 0.05 minus 2, right? So because there are 2 periods passed. So it will go until that last payment will be plus 0.05, right? Minus 10, because that last $100 is paid after 10 years. Okay? So again, you could use Excel to calculate this present value of annuity. So in this case, again, we have that structure, which is annuity, because we have the same payment, each made after the same interval of time, and also the rate is the same everywhere, right? So if we use Excel now to calculate each of those present values separately, add up, you will come up with that calculation, which will stand for that loan you're taking today. Okay? So again, good news is that we don't have to go into that process. We can simply use a formula which mathematicians have developed for us and which will do the same job as, you know, adding a lot of payments, but it will do it with much higher efficiency. So what formula am I talking about? So this formula is present value of annuity is equal to PMT, which is payment. The same thing, it will be $100 later on, right? It will be 1 minus 1 plus I minus N I. Okay. So that's how that formula would look like. It's kind of similar to the present value of annuity that we discussed earlier, but there are major differences here. You can see that we have a couple of minus signs appearing, and you need to be very cautious about that. Now, how we would use that formula for this particular example? Again, our payment is $100. Our rate is 0.05 for I. So this I is 0.05 because it's compounded annually rate. For that compounded annually rate per period is 5% rate per period, and there are 10 periods, right? So minus 10. And here we also have 0.05. So if we use that formula like that and we put values in, we can follow BADMAS and calculate this present value. When you follow BADMAS, keep in mind it's negative exponent here, so you have to appropriately use negative exponent in your calculator. It is important for you to practice calculating these. Going forward, we'll have a lot of calculations like that. So it is important to practice a lot with using calculator for computing these present values or future values. So it's $772.17 if I round to 2 decimals. Okay. Now, in this example, you can realize that that's actually the loan you can take. If that is the rate, so that's the loan you can take today, for which in future you will have to pay 10 payments of $100 each payment made at the end of every year, right? So that's the loan. Now, I want to speak a little bit more here for you to realize how that loan will actually work. So we already know that this PA is going to be 772.17, right? So you take this loan today. Then you need to realize that this loan will start accumulating interest, which is 5% compounded annually. So after first year, 772.17 will accumulate 5% of interest, right? So when that happens, you will pay your first $100 towards that loan. This first $100 will pay part of this loan together with already 1 year worth of interest. Whatever will be remaining will again accumulate 5% interest, and then you will pay that next $100 towards that loan. So that process will continue until it will be the last $100 for you to pay, which will pay off the loan completely at that moment. So after 10 years, there will be nothing left of the loan, right? So what this means is that the total interest you will pay over the course of 10 years is calculated this way, right? So for this loan amount. Of course, it will be all the money you pay, which is $100 times 10, which is $1,000. You pay $1,000 in total towards that loan. You can subtract the actual loan amount, right? So that will be the interest amount that you will pay towards that loan. Okay, so this example shows what the present value of annuity looks like. Now we'll continue into investigation of annuities in a more general, from more general perspective. So we'll define annuities a little bit more strictly, then we'll remind ourselves what the formulas are like, and then we'll consider several examples as to when you should use the formulas and when you should modify those formulas for some cases. So let's go ahead and investigate those issues. Okay, so what is annuity generally speaking? What kinds of annuities are there? Let's explore that. So we take a timeline. So we have a timeline. On this timeline, we have time 0, which is today. Let's consider some time into the future, which we'll call plus first period. Plus first period. So what that means is that it's one period into the future. It could be 1 month into the future, it could be 1 quarter into the future, it could be 1 year into the future, whatever. So then we'll have plus second period, right? So this is the same period, okay? So when we quote here periods, it's going to be the same period. So if this first period is plus 1 month into the future, so the second plus the same plus 1 month period into the future, right? So each period here, duration is the same, always the same. And so it will be continuing plus nth period. So what is important to realize is that this duration is always the same, right? For example, it could be plus 1 month, plus 2 months, plus and so on, plus nth month, okay? Or it could be plus first quarter, plus second quarter, and so on, plus nth quarter. It cannot be like this, plus 1 month, plus then 1 month, 3 weeks, and so on. So these periods of times cannot change from one to another. So at the end of each period, we are having some payment. At the end of each period, we're having some payment. So of course you realize there are n payments in total. Now we also have to talk about some periodic rate I. Periodic rate I. So over each period we have rate I to talk about. So for example, if you have some rate compounded monthly and if each period is 1 month, so for each period you have that monthly rate working here. Okay, so after you have drawn the structure, you can call the structure an annuity. Okay, so when an annuity is the structure, or we also call it a financial instrument, where there are same payments made or taken over the same intervals of time, and when the periodic rate is the same for each period, right? So 3 conditions we need to have for this to be an annuity. So first condition is same PMT, right? Same payment. Second condition is same time intervals. And third condition must be same I, right? Same I over each time interval. Now, that's important because if one of those conditions is not satisfied, you cannot really, strictly speaking, about one annuity at least, right? So it could be that you will speak about several annuities. For example, it could be that for the first 5 years you had, let's say, 5% compounded monthly rate. And then for the other 5 years, it could be now 6%, could be having 6% compounded monthly. You see, in this example, your 5% rate would change to 6% rate, and as a result, your annuity would change to another annuity. So now my Siri, for some reason, thought I'm addressing. Okay, so as you can imagine now, you should look for these three conditions to make sure that you have an annuity. Of course, outside of our course, we can speak about other annuities which could still be treated as annuities, where payment is not the same but growing based on some condition. Also, it could be that the rate is not the same in each interval but growing with some condition. So this could be also annuities. But in your course, you should not worry about those more complicated examples. We always will speak about an annuity if we have this kind of three conditions. Okay, so now if these three conditions are satisfied, you have an annuity. Now we need to speak about various types of annuities that we can encounter. At first, it could be that it is not very clear what we're talking about when we discuss those types. But when we consider examples, it will be more clear. Okay. So now, after this, let's talk about types of annuities. So first type of annuity we'll talk about is a simple annuity. Simple annuity. Now, in a simple annuity, your payment frequency is the same as your compounding frequency. So in a simple annuity, the frequency of your payments is the same as the frequency of your rate compounding. Now, let's have an example. So you pay into your savings account some amount at the end of every month, right? So if you pay at the end of every month, your payment frequency is 12 per year, right? If at the same time your rate, which bank gives you for your investment, if that rate is also compounded monthly, so let's say if it's compounded monthly, which means 12 times per year. So if that happens, annuity is simple. So you pay 12 payments per year, you pay every month, and also your rate is compounded monthly. So that is the situation when you have simple annuity. We'll see in examples also how that will look like. Okay, so now another type of annuity that it is important, which is highly important for us, is general annuity. Generally. So general annuity is pretty simple to define, and that is general annuity is not a simple annuity. Now, what it means is that if annuity is not simple from the point of view of the definition of the simple annuity, so then that annuity is general. For example, your payments can be every month, right? So you can have 12 payments, PMTs per year. You have 12 payments per year, but the rate could be, let's say, compounded quarterly, right? So compounded quarterly means 4 times per year. So if you have 12 payments per year, but your rate is compounded quarterly, so that is the example of a general annuity, because it is not a simple annuity from the point of view of the definition of the simple annuity, right? So the number of payments per year does not coincide with number of compounding periods per year. So that is a general annuity. So which follows from here that you cannot have simultaneously simple general annuity. That cannot happen because these are mutually exclusive definitions, right? So next type of annuity that we'll talk about, okay, you know what? So after we speak about these two types, we'll speak about other two types right now. So we'll have now third possibility for an annuity is of a little bit of a different kind than simple and general possibility. So in that case, we have PMTs. Okay. So we'll talk now about ordinary annuity. So if we have an ordinary annuity, PMT payment is made at the end of each time interval. Which means that in ordinary annuity you pay at the end of each time interval. So far those examples that we talked about, they were the examples of ordinary annuity because when we saved our amount, you remember when we paid $100 in the account, that was done at the end of each year, so at the end of each period. So when you pay your payment at the end of each period, so that is going to be an ordinary annuity. And finally, we'll have a due annuity. Due annuity. So due annuity is when payment is made at the beginning of each period. So it looks like due annuity is simply not ordinary annuity. You remember how we defined general annuity as not simple annuity? So it looks like due annuity is not ordinary annuity, but it's not really the case. If annuity is not ordinary, it's not necessarily automatically a due annuity. Because if the payment is not made at the end of each period, it is not necessarily that it's made in the beginning of the period, right? So for example, the payment could be made in the middle of the period or at some other time in between beginning and end of period. But in our course, we are not going to consider those situations. We always will have payment either at the end of the period or at the beginning of the period. So we don't need to worry about that. So from the position of our course, if the annuity is not ordinary, it is most often will be due unless there is a specific mention that the payment is some kind of a weird, it's in some kind of weird time, which is in between. We usually will not have problems like that. So in our problems, the payment will be in the beginning of the period or at the end of the period. Okay, so we'll have either ordinary or due annuities. Now, so we have discussed 4 types of annuity. It is possible to combine it is possible to combine types of annuity, but not always, right? As for example, you cannot combine simple and general annuity in one existing annuity. Or you cannot combine also due and ordinary annuity in one existing annuity. But you can combine annuities in, for example, due simple annuity. So that could be possibility, right? So annuity could be due and simple. For example, in that annuity, you would have payments in the beginning of the interval and also the rate compounding frequency would be the same as your payment frequency. So it could be that the payment is at the beginning of every year, and the rate also is compounded annually. So that would be a due simple annuity. Well, there are other possibilities to combine annuities, right? So for example, you can have ordinary, general annuity. So it could be ordinary general. For example, so the rate compounding frequency might be different from payment frequency, but payments could be made at the end of each period. Okay, so it is possible to combine types of annuity to form some interesting annuities, but we'll talk about that in future using various examples. So our major annuity is actually the major annuity. So let me just write it like this. So major annuity is ordinary So the major annuity is ordinary simple annuity. Why is it a major annuity? Because that will be the type of annuity that we will always come to whenever we solve for any other type. So any other type of annuity will eventually come to this ordinary simple annuity. And what is absolutely important is that for this major ordinary simple annuity only, we have those formulas, which we already saw. So future value will be payment. Here it will be 1 plus I n minus 1 I. And for present value will be PMT 1 minus plus I. Okay. So we'll have these two formulas, one for future value and another one is for present value. But one important, very important point to keep in mind is that future value and present value formula. Now I dropped those future value of annuity. You remember how in those examples I was writing like this, future value of annuity, right? So I drop it for now because there is no any confusion here between this future value and any other future value. We're talking now only about future value of annuities. So these two formulas for future value and present value of annuities will be only valid for ordinary simple annuity. Okay, so if you have any other type of annuity except ordinary simple, you will not be able to use these formulas directly. Okay, so there will be some necessity to make some modifications to your solutions for your solution to be able to use one of those formulas. So, important point, make sure to understand that these formulas, future value and present value formula, are only valid for ordinary simple annuity. That is, for the annuity where each payment is at the end of each interval of time, and also rate compounding frequency, so how many times the rate is compounded per year, that should be the same as your payment frequency, which is how many payments you pay or collect per year. Now, we will start exploring these ordinary simple annuities, and then we'll proceed to other types. But for start, it will be our first important discussion, ordinary simple annuities. So what we'll do next, we'll consider several examples which will highlight how you would use these formulas for ordinary simple annuities. For our first example, we have John, who invests $750 at the end of every month into a savings account for 8 years. Interest rate is 5% compounded monthly. How much will John collect at the end of 8 years? So, in this example, we have to identify first if we actually have an annuity, right? So, is it annuity? Well, let's think about it. We have now a timeline here. So for our first example will be detailed. So we have time 0, right? So then John invests 750 plus 1 year plus 1 month at the end of every month, right? So it's every month. So plus 1 month, plus 2 month, plus 3 month, and so on. So that will continue for as many months as necessary, but at the end of each month, John has these payments which he makes towards his savings account. So that will be continuing until 8 years will be over, right? Plus 12 times 18, 12 times 8. Okay, so it's 96 months. So let me just write it here, plus 96 months. Again, it will be 750 payment. So remember when we talked about annuity, we had to identify if it's the same payment, which it is, so it's $750 every time. Also, if the time interval is the same, which it is, so every time it's 1 month interval, right? So it's the same interval of time. Also, we need to identify if the rate is the same. And yes, the rate is 5% compounded annually everywhere, right? So throughout the whole 96 months, it's the same rate. So we do have these 3 conditions satisfied, and we have an annuity. Now the next thing is to find out what kind of annuity that is. So look, we have here very important keywords. So first keyword is here, at the end of every month, right? So this payment is made at the end of every month, which makes our annuity. So let me erase this now. So this at the end of every month makes our annuity ordinary. Okay, and then another condition we need to really check, another a couple of keywords to look for is this. This rate is 5% compounded monthly. So this rate is compounded every month, which means 12 times per year, right? And the payment is also at the end of every month. So we have 5% compounded monthly, 12 times per year, and the payments are also every month. So 12 times per year, which makes this annuity simple. Okay, so this is how you would analyze the type of annuity. It's ordinary simple annuity. And because that is ordinary simple annuity, now, just as another kind of reminder, because to our first example, maybe I should say, so why again we decided it's ordinary? Because at the end, right? So at the end. So the payment is at the end of every month. And why is it simple? Because the rate is compounded monthly, so this 5% is compounded monthly, right? So which is 12 per year, right? 12 per year. And also it's at the end of every month, so each payment is also every month, right? So PMT every month, which is also 12 per year. So here you see 12 for rate, it's 12 per year, and for payment is 12 per year. So 12 is equal to 12. Therefore, this annuity is simple. I just wanted to, once again, to make sure to show you how you would go about this analysis to find out that annuity is ordinary simple. So that is ordinary simple annuity. Okay. Now, because this is an ordinary simple annuity, you can use one of those formulas that we talked about. And now we need to decide which one we should use. Is it present value or is it future value that we need here? So here we're talking about accumulation process, right? So John wants to collect the amount at the end of 8 years. So that is the accumulation process, which means that we're looking here for future value. Okay, so future value of annuity is PMT 1 plus I n minus 1 divided by I, right? So that's the formula for future value, and we can use this formula because that is the simple ordinary annuity. For that reason, we can use this formula. To use this formula, we simply need to use our actual payment, which is 750, instead of PMT. Okay, so then we need to ask ourselves, what is this I? I is our rate per period, right? What is our period? Is a month. Now, our nominal rate is 5%. So 5% per year, nominal rate, divided by 12, number of months in a year, right? So that will give us the I, periodic rate. Okay, what is N? N is the total number of payments, total number of periods in this problem, right? So we have now 12 payments per year times number of years, 8, right? So N is the total number of payments. And we have here 12 times 8 payments in this case, okay? So, which is 96. Now let's put all this data into this formula and see how this formula will look like after we put all that into the formula. So I'll write it completely. 9 times 8 minus 1, 0.05 over 12. So, just for convenience, I put it in the bracket like this too. So that will be the totally, constructed future value based on that formula. Now I can erase this because now we got where we took these items from. So now we need to follow BEDMAS to really compute it. Now you can use your calculator to compute separately that I, separately that N if necessary, and then put it all together. Or you can just put everything in this formula and compute the future value, just using this, like all this structure right away. So it appears to be 88,305.38. So I find it particularly convenient for me to calculate this periodic rate, 0.05 and divided by 12. Then what I do, I keep that in the memory of my calculator. For example, I do 0.05 divided by 12, do STO 1, which will put in the memory of my BA2 professional calculator. And then I'll go from there, right? So I'll do plus 1, then I'll take that exponent, which is 96. I already know it's 96, but if I didn't know, I would compute it separately and put in the memory of my calculator somewhere in another place, let's say STO2. So then after I compute that, will be minus 1 and divided by this periodic rate, which already is saved in the calculator, okay? So that's how we find this future value based on this formula. Just plug things in, very carefully calculate this. Calculation process is something that you really need to train yourself to do properly, and that will be the future value of this annuity. Okay. Let's now check out another example. In our next example, we'll be looking for present value. So let's ask this question. What loan amount could you take if you have to pay $3 at the end of every day for 9 years? Assume that the interest rate is 4% compounded daily. This structure is not as common as, paying for something every month or every quarter or even every year, but just to practice with various rates, and also just to keep in mind that in finance we can encounter various situations. So in this case we have to pay at the end of every day, and also the rate is compounded daily. So let's analyze this annuity. So our keywords are these. So at the end, right? So we pay this amount, $3, at the end of every day, which means that the annuity is ordinary. So this annuity is ordinary. Now, also let's check out another set of keywords. So we have here every day, right? So the payments are every day. Every day. Well, every day means 365 per year, and also the rate is compounded daily, which is also 365 per year. So the payments are having frequency 365 per year, and also the rate has the frequency 365 per year, which means that this annuity is simple. It is an ordinary, simple annuity. Because that's ordinary simple annuity, we have the complete right to use one of those two formulas for future value or present value. Now the question is, which one of those should we use for this problem? Well, this problem is about loan amount, right? And loan amount means that you are taking that loan usually before you pay for it, right? So this loan amount is something you take, for example, today. So that's money in your pocket today, but your payments for it, so this $3 at the end of every day, will happen only later. So for loan amounts, we're having to deal with present value of annuity, right? So present value is the formula we're interested in. So we have payment 1 minus 1 plus I minus n I. And that's our formula for the present value of annuity. Now, of course, we will put things in. PMT is $3, so you pay $3 for that loan, and that's the payment. Now I, but let me put it separately here. I is 0.04 divided by 365. Right? So that's periodic rate in this case. Next is N. What is the total number of periods? Total number of periods is, of course, 365 times 9, because there are 365 days per year, and there are 9 years. Right? So let's, if I put all that in, I can calculate these separately and then calculate this present value, but just for you to see all completed and also to get used to that level of complexity, let's put things into this formula and see how this formula will look like after we put all these numbers in. $65 minus here 365 times 9, and here we have 0.04 divided by 365. Okay, so that's what it will look like, which again we have to calculate using our calculator very carefully, following BADMAS, using memory of the calculator a lot. So this could be a way to efficiently calculate this present value. So let's do it. So this calculation leads us to 8,275.73. So we have 8,275.73. That's the amount of the loan. Just something to keep really in mind here, to be very careful about, is when you calculate this, you need to keep all decimals always, without rounding. So you should not round yourself. Let your calculator keep as many decimals as possible, and because this calculation is very sensitive to decimals, right? So when you calculate this, keep that in mind. Okay? Otherwise, your calculation will not be right. So that's the present value of this problem, and that's the loan amount we're looking for. Here is our next problem to discuss. We'll push this problem a little bit further for us to see some other parts which we might be requested to find for problems like this. So in this problem, we have Amy who would like to accumulate some amount for her vacation. For this, she will invest $500 at the end of every 3 months into an account earning 6% compounded quarterly. How much will Amy accumulate at the end of 3 years? Well, let's analyze this problem. Already you can see here with the red keywords are underlined. So you have at the end, which means that this annuity is ordinary, right? So the payments are invested at the end of every 3 months, right? So at the end means the annuity is ordinary. Now every 3 months means 4 times per year. 4 times per year. Or the payments, in other words, are made quarterly. And the rate here, 6%, is also compounded quarterly. So we have 4 times per year that the rate is compounded. So now we have payments which are made at the end of every quarter, and the rate which is compounded every quarter. As a result, this annuity is simple. So this is an example of ordinary simple annuity. So we can use our future value formula, because that's ordinary simple annuity, and we can use that formula directly. And it's future value, obviously, because that's the accumulation process. And we are asked about that amount at the end of the term of this annuity. Okay, so now let's calculate that future value. Now we can right away put our values in. So we have $500 for our payment. Then we have 1 plus I. So I is going to be 0.06 divided by 4, because that's a quarterly rate. So now we have 4. That's the total number of payments. So that's the term. So 4 times 3, right? So because there are 3 years. So we have 12 quarters in total, minus 1. 0.06 divided by 4. Okay. Now I already used that formula directly. I didn't write that formula separately, because now we already had those examples where you could see how we would plug values into our formulas. So what I invite you to do is to have some formula sheet printed out, write down formulas separately, so that you can see how these formulas look like every time you look at how we use those formulas. So now it's a calculation time. Let's go calculate this. So I obtained 6,520.61. Okay, 6,520.61. That's the amount of money that Amy would accumulate after 3 years. Okay, so what I want now to do is to ask another question. How much interest will Amy earn? Okay, so let me keep this future value already calculated on this side. So that's the future value that we'll have at the end of 3 years. But I want to ask this question now. Another question is, how much interest will Amy earn? So how do we find that amount of interest? In order to find amount of interest for an annuity, we need to compare how much money will be accumulated with how much money will be paid, right? So interest amount will be future value of annuity, right? So in this case, we're dealing with future value. So interest will be future value minus PMT times N, right? So what this means is that you take future value, the amount accumulated, minus all the payments combined for this annuity. So there are N payments, and you multiply your payment, each payment by N to find that total amount of money that you actually paid towards that account. So in our case here, Emmy accumulated 6,520.61, and from here we'll be subtracting all the money that Emmy paid, which is 500 times how many payments were actually in this. So we have 4 times 3, right? 4 times 3, because Amy paid $500 4 times a year for 3 years. So you can see that this part here is actually N, right? So that's 12 total number of payments. Okay, so let's calculate this. 520.61. So Emmy will earn $520.61, so $520.61 of interest in this structure. Okay, here is our next problem. Samir financed a car by paying $800 at the end of every 6 months for 5 years. If the rate is 7.25% compounded semi-annually, how much interest will Samir pay for this arrangement? Okay, so in this problem, again, let's very quickly analyze the problem. So we have that the $800 is paid at the end, which makes the annuity ordinary, and then the payments are made every 6 months, which is twice per year, 2 times per year, and the rate is compounded semi-annually, which is also twice per year. So we have 2 times per year for payments and 2 times per year compounding for the rate, which makes the annuity simple. So it's again ordinary simple annuity, which allows us to use our formulas for annuities. Now, what kind of formula we need? Do we need future value or present value? In this case, Samir finances a car, which is a type of loan, right? So Samir will drive a car already starting today, but for that car, he will be paying at the end of every 6 months in future, right? So that, because it's a loan, we're talking here about present value of annuity. So in order to find in order to find interest, we need to find present value first. Without finding present value, we'll not be able to find interest for this problem. There is no formula which directly gives you interest for future value or for present value for annuity. You have to find those first. So let's find present value for this problem. So present value is going to be $800, which is your payment. Okay, so it's 1 minus 1 plus 0.0725 divided by 2, because the rate is compounded semi-annually. So the exponent is negative 2 times 5, right? Because 2 times 2 semi-annual periods per year, and there are 5 years. So in total we have 10 payments happening in this annuity. And we also divide that by 0.0725 divided by 2. Okay. So let's just now calculate this. $6,000 611.56. 6,611.56 rounded to 2 decimals. That's the present value. Now let's talk about interest. How do we find interest? Well, interest amount in this case will be all your payments times n, right? So all your payments combined, each payment multiplied by the number of payments, minus the okay, if we talk about the formula, present value. Okay. Why? Because you're paying for your loan later on, right? So those payments will contain interest. Of course, when you pay for your loan in future, you pay for that loan amount plus interest accrued. So all your payments will contain interest, which means that all your payments combined will be bigger than the present value, the loan amount. It's just a natural thing to have, right? In a loan transaction. So therefore, you take all your payments combined and subtract the loan amount. That's how you will find your interest amount. Okay, so now we take our payments combined, which is 800 in this problem, times 2, because there are 2 payments per year, times 5, because there are 5 years, and we subtract from here 6,611.56. So let's see how much that interest is equal to. 1,388.44. So that's how much interest will be paid for this loan amount. Okay. Now, of course, in this situation, I have to admit that this is a very abnormal situation, because usually when you finance a car, you pay first of all at the beginning of every period, and also when you finance a car, usually you pay every month. Okay. And also, when you finance a car, maybe the amount will be bigger. But sometimes different things can happen. And let's say this is a used car market. The car price is cheaper, and we also have some special arrangement which allows payment at the end of every 6 months. So we should be ready for anything in our financial mathematics, and that's the kind of problem we have. Okay, so that's how we find interest for this problem. Now, just to once again, just to make sure we understand how interest works in this kind of situation, you need to realize that, you see, there is some loan amount here, which is a present value of annuity. So that loan amount for which you will be making payments. So plus 6 months, you will have your first payment. Okay. Then plus 12 months, which is plus 1 year, you will have another payment. So each of those payments are equal, right? Which is $800. So this is $800, and this is $800, and so on, right? So we have the same kind of payments. And plus 5 years, right? At 5 years, your last payment also will be $800. Okay. Now, what is important to realize is that each payment contains interest. Okay, because once you take your loan, that loan will accrue interest, and in every payment you will pay that interest. Okay, because your first payment has to pay for all interest accumulated for that loan. It will contain the biggest amount of interest. Okay, so your first payment will pay, so this red will be your interest for the loan, right? So this red part will be some interest that you pay for the loan, and the remainder will be going towards that loan actually, right? So now after that first payment, what happens with that loan? Well, interest is just what you paid for. So interest part you just paid to the bank for having that loan, but that remainder will go towards principal of that loan. So that principal will become smaller by that principal repayment amount, right? So now at this moment you will have a smaller principal, which also will accrue interest for the next period, and then for the next period you will have less interest included in the payment. Why less interest? Because now that new principal, which will happen after 6 months, will be a little bit smaller because you already paid it out a little bit. So now next payment will contain just a bit of smaller interest portion, and so it will go until almost all of your $800 will go towards your loan, and interest will be just very slight portion of this last payment, right? Almost all of it will go towards the loan, and the last payment will completely close that loan. So that's how the process would look like. Okay, but all your payments combined will contain all that interest that you pay, right? Combined, and that's how we found that interest for this problem.